Aloha and welcome. In this video, we're going to be talking about trees. Specifically, we're going to be talking about binary trees. So let's go ahead and open up our text. So we're talking about binary trees here. And binary trees are essentially trees that have up to two children. They can have zero, they can have one, or they can have two children. And we call those children the left child and the right child. So there's a number of terminology that we need to learn here. The first one is leaf. And a leaf is a tree that has no children, nothing on the left and nothing on the right under it. We have internal nodes, and internal nodes are essentially nodes that have at least one child to them. We have the root. The root is going to be the top node. It's all the way up at the top of everything. You can have, again, with the top node, you can have 0, 1, or 2 children. If the root has no children, therefore the tree is the only node. The root is the leaf as well. So if it's not a leaf, then it's considered an internal node. In other words, a node that has any children, any meaning one or more. So then we have the concept of parent, and a parent is a node with a child. It's a node with a child that's the child's parent. So we also have ancestors. Ancestors are going to include the node's parents, the parents' parents, etc., all the way up until you get to the top of the tree, the root of the tree. And a node's descendants is what you'd think it would be. It would be the any of the node's children or the children's children going all the way down to the bottom. So we're looking here at the participation activity. It's going to show us a little bit about this. It's going to show us linked list versus binary tree here. So saying here that in a linked list, each node has up to one successor. In other words, A only has B after it, B only has C after it, D only has E after it. So when we look at a binary tree, each node has up to two children. So you look over here, A has C and B, then B has E and D, C over here has G and F, and then D and E and F and G, they have no children. So tree is normally drawn vertically. So you've got the up at the top, this is where your root node is going to go. And the edges over here, these are known as these are called edges. We'll learn about that in a moment, but the edges are the arrows that we have going between or not really arrows, but they're the connectors between each of these nodes. So node, it can have a left child or right child, and a node with a child is called the child's parent. So going through here, you've got first node, you've got the root node, you've got node without, hold on. Okay, yeah, so it's divided this up. So you've got your root node up here, you've got A, you've got internal nodes, which are like C and B. You've got parents here. So B is a parent of D and E, C is a parent of F and G. Your leaf nodes are the ones down here that have no children under them. And you can see that B's left, the D here is B's left child, and E here is B's right child. So we're going to look at a participation activity, binary tree basics. So you look at this one over here. It looks pretty evenly here until you get over here to Gupta, you have a carving under it. So which node is the root node? That obviously is going to be Jones up here. Then Smith's left child. So if we look down to Smith, the left child is going to be Kumar. So go ahead and answer questions like this. It's pretty straightforward. We're going to talk about the depth, the level, and the height. So some more terms we have here. So as I mentioned before, that the connectors between the nodes that connect a node to its child is called an edge. A node's depth is the number of edges on the path from the root down to the node. So if you want to talk about, let's say on up here, if we're looking at this, we'd say that Smith, it has a depth of 1 because it's, from Jones down to Smith, it's 1 down. So, a node's depth is the number of edges on the path from the root to the node. So you can get that by counting the edges between the two. And for the root node, we've got a depth of 0 because it's right there at the top. All nodes with the same depth have what we call they're on the same tree level. So if you look at the tree back up here, Smith and Adams are on the same level, Kumar, Lee, Gong, and Gupta are on the same level. Even if they're in different branches, they're considered the same level if the depth is the same. So a tree's height is the largest depth from any node. So a tree with just one node has a height of 0. So if we were to look at here, if it was just the Jones, it would be 0, but then it's 1, 2, 3. So you have a height of 3 on this tree. So looking at this participation activity, we've got binary tree terminology, height, depth, and level. So if we click start here, binary tree has edges A to B, A to C, and C to D, as you can tell with the orange markings here. Clicking on, a node's depth is the number of edges from the root to the node. So you can see that we have depth of D here is 2. The depth of B and C is going to be 1 because it has that one edge between A and B and A and C. And then the depth at A, which is your root, is 0. So again, we talked about this up above, but the nodes of the same depth form what we call a level. So A is one level, then B and C is on another level, and then D is on another level, and they have separate depths. So tree's height is the largest depth of any node. So if you go in here and you look, you go A to C to D, that brings you down 2 levels to the tree height. That's the deepest level, so that's the tree height of 2. Then participation activities, we've got another binary tree height, depth, and level. So A's depth is 1. So A is actually the root, so it's going to be 0. So we're going to have to say that's false. E's depth is 2. So A, this is a depth of 1 to 2. That is correct. So go ahead and answer these, go through those. So this is something that's a little bit, it takes a little bit of thinking. So go ahead and ponder on these different definitions. But first of all, a binary tree is considered full if every node contains 0 or 2 children. So if every node within here contains 0 or 2 children, it's considered full. So we look at this, the first one here, and we're going to say, does every node have 0 or 2? This one has 2 children. 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 This one has 0, 0, 0, 0, 2. Oh, we have 1 and 0. So because this one has 1, it's not considered full. If you look over here, this one over here, again, has just 1, so that's not full. Over here, you've got this one that has 2. This one has 2 below it. This one has 2. This one has 0, so 0 is okay. So essentially, full means you don't have a partial. Everything has to have, 2 on them. So you look over here, this is not full. This one over here is full because everyone that can have 2 has the 2. And over here, it's also full as well. So complete means that if all levels except for possibly the last level, remember a level is all the nodes that make up one certain one, they're all parallel to each other. If so, complete is if all levels except possibly that last level down here contains all possible nodes, and all nodes in the last level are as far left as possible. Okay, so when we look at this, we're looking at this one right here, and this one is complete because if you look at it, you'll see that everything except possibly the last level, which is down here, contain all the possible nodes. So there you go. So this one is complete. If you look over here, you're going to find that this one is not complete. Why is it not complete? Well, if we take that definition again, it's going to say that everything except the last possible level is not full. So this one is not full. It doesn't have a right element. This one over here did have a right element, but it didn't have the last level here. So that's why this one is complete. This one is not complete because it does not have at this point, a single terminating node or a leaf at the last level. So anyway, it needs to have that here in order for this to be considered complete. So another definition we have to know is perfect. And a binary tree is perfect if all internal nodes have two children and all leaf nodes are at the same level. So if we look through here, you'll see that this one is not perfect because all internal nodes do not have two children. So this one right here does not have two children, and all the leaf nodes are not at the same level. So this one right here is, it's a leaf node and it's not at the same level as these. So you look in here, the same thing, it's not perfect. You look over here, same thing, not perfect. Look over here, it's not perfect because these don't have two. So if you look over here, this one's also not perfect because you have one over here, but this one over here, you'll notice that it has all of them. So this one is perfect. This is the only one that's perfect on the whole sheet. So get used to those definitions. They take a little bit of thinking, but go ahead and look through them. Look and see what does it really mean. What is it that we're looking for when we're looking for something that's complete, when it's full, when it's perfect. And then down here in the participation activity, I want you to identify the special type of binary trees. So if we were to look at this, one of the first things that we can do, we can go ahead. We need to match up like the different ones with the tree 1, 2, 3, and 4. So looking at this, so we'll go ahead. We'll review the word full. So full is if every node contains 0 or 2 children. So if we're looking for everyone that has 0 or 2 children, we're going to find that this one does not have 0 or 2 children for every node. This one does have 0 or 2 children for each one. So this one is going to be considered full. So this one over here, this one is not, 0 or 2 children. So 0 children, 0 children, 1 children. So this is not. So this could be full. So it starts with full. Is this one complete? So then we look at the definition of complete again, and it's if all levels except possibly the last one contain all possible nodes, and all nodes in that last level are as far left as possible. So when we go in here and we take a look at this one, again, is this one complete? I believe this one right here is complete. So we have full and complete. So if we were to take full and complete, try this on for number 3, we would see that that is correct. So go ahead and go through your definitions and look at each tree and see, does this fit that, description, and, go through it full, complete, and perfect, see which ones match up. So, so that should take you a while to go through. Binary trees, let's go here and look at it. This is our challenge. So we start this. What is the root node? Our root node is D. It's easy enough. What is the parent node of H? So if you look at H, you go and find the parent. The parent is going to be L. And then what are the ancestors of the node H? So if you look at H, the ancestors are going to be L, K, and D. So I don't know. All right, L, K, D. Then what are the leaf nodes? So I'm not sure if they're referring to the leaf nodes of everything in here, or I guess they are. So if we look at these, a leaf node is one that doesn't have any children under it. So we're going to say J, F, C, G, H, and N, because that's all of the leaf nodes that do not have any children. How many internal nodes does the tree have? So how many internal? So if we want to remember what internal nodes are, we're going to go all the way up to the top. And remember that an internal node is a node with at least one child. So it's a node with at least one child. So if we go back here and we take a look at this, how many internal nodes do you have? This one has more than one. So we've got this one that doesn't. So 1, 2, 3, 4. This one does not. 5. So we put 5 here. And we've got incorrect answers. So expected, D is the root node. We got that. L is the parent of H. L, K, and D are the ancestors of H. So we look at this, L, K, and D is incorrect. And I'm not sure why exactly that is. I'm guessing that L, K, and D, they just want, is it, hold on, parent node, ancestors of node H would be L, K, and D. I don't see why that's not correct. Oh, down here, the ancestors of node H are the parents, the parent of node H, the parent's parent, and so on up the root. So the ancestors H are L, K, and D, which is exactly what we put in there. So I don't understand why they are not accepting that. It did have commas in there, so yeah, so we're correct there. All right. So then nodes J, G, J, G, F, C, H, N, J, G, F, C, H, N, we have that as well. And the tree has 5 internal nodes. So we actually got them all right. I think. Oh, wait. Oh, LKD is the only one that it's marking as wrong here. So LKD. And that's actually correct. So LK and D, I don't understand why they are marking that as incorrect. Oh, I see why. Here it is. I have put in a period there instead of a comma. I don't understand how I did that, but my apologies. So all this is correct. Go ahead and click on next and go through the next ones, and you'll, yeah, that'll be a good exercise for you. Anyway, subtree, a binary tree subtree is any node X in the tree and all of X's descendants. So node X is the subtree's root, and the subtree itself is a valid binary tree. So if we look in here, we can see, for example, subtree with one node, I is a subtree with one node, subtree with 3 nodes is this one right here. So you've got E, J, and K. Then you've got subtree with 7 nodes. You've got C, F, L, M, G, and O. So participation activity. So we look and see, is the highlighted part in the tree below a subtree? Yes, it is. And why is it? Because a subtree is any node in the tree and all of its descendants. So it is, when we're looking at this, is the highlighted part a subtree? Yes, we have it and all of its descendants there. So yes, it is. And I'll let you do the other ones here. I'll do this one here. This one is not a subtree because they're not connected there. They are not direct descendants of each other. So when you go in here, the highlighted part cannot be formed by taking one node X and all of X descendants from the original tree. Removing the unhighlighted part reveals the result is not a single binary tree. So it's not in the same, they're not connected. So go ahead and do the rest. And that is all for binary. Well, it's not all for binary trees, but that's all we're going to be covering in this video. If you have any questions, feel free to ask me. Send me an email or give me just request a meeting. But keep up in here. I want you to know your terminology here: leaf, internal node, root, parent, ancestors, descendants. Those are fairly easy to understand intuitively. Edge, depth, level, and height, again, it's not that difficult. The ones that are going to be a little bit difficult to remember is full, complete, and perfect. Understanding what those terms mean, keep that, go ahead and study that. Work through your examples here to figure out and understand that. Then over here, you're going to get exercise with understanding roots and descendants and things like that. So internal nodes. And then subtrees are pretty understandable. It's a section and all the things that come under it. So yeah. So again, if you have any questions, feel free to reach out. I'm here for your emails and can set up meetings with you. Other than that, have a good day and I'll see you in the next video. Aloha.